Okay, thank you. Thank you for giving me a chance to give these lectures here. So what I'll do is, so Samit gave a nice overview of these two theorems that we proved and a sketch of the proof. My plan is to just give details of the proof of the first theorem, okay, the Brumer-Stark conjecture. And many ideas that go into the proof of the second theorem are similar, but I'll not talk about that at all. Okay, so let's recall what the statements that we had. So F is a totally real field, H is an extension of it, S was a finite set of places of F, which contains all the ramified places and all the Archimedean places of F. T was a non-empty subset of places of F that's disjoint from S, and T is large enough. So T contains a prime of residue characteristic bigger than, let's say, degree of F over Q plus 1. Okay, something like that. Or it contains two primes of distinct residue characteristics. So that's also good enough. In this situation, the theorem that we are interested in, is that the Stickelberger element ST theta of H over F, this is contained in the annihilator ideal of the T class group. Okay, so I think all these was defined, so I'm not going to recall the notations. And the minus here means 2 is already inverted. Okay, and I'm taking the minus part, the part on which complex conjugation acts as -1. Okay, so that was that's the Brumer-Stark conjecture away from p equal to 2, and that's what we are interested in proving. Now, as Samit pointed out, we have to go through generalizations of refinements of these. We have to get a refined statement, and only then our methods work. So the first refinement was that this theta st H over F with a hash. So I think this was not defined by Samit. So I'll tell you what it is. This is contained in the fitting ideal of the T Pontryagin dual of the minus part of class group. Okay, and this hash is simply some involution on ZG, which is a ZG linear map given by G going to G inverse. And so this is the statement that we write down in our paper. So I'll state it in this form. This is not inconsistent with whatever Samit said, because we did not tell you what the action on the Pontryagin dual is. Right? If you take the natural action, because G is abelian, you can remove this hash, and this is what Samit meant. But if you take the contragradient action, which is the natural thing to do, then you have to put this hash. And since the paper is written with a hash, I'll stick to this. Okay, so this is not inconsistent with what was said. It's just, you have to interpret it properly. The action was not made explicit. Okay, so I'll tell you another refinement of this conjecture, which Samit did not state. This is a conjecture of Kurihara, and for this I need to define the Sinnett-Kurihara ideal. This is defined to be the ideal of ZG, which I denote like this. This is, let me write down the thing and then I'll tell you what it is. So now this is the set S I take to be just the Archimedean places. Okay. So so what does this mean? This means that whenever I evaluate this element at chi, I get only the I get the L function which is primitive away from the infinite places. Okay, so only the Archimedean places are missing. V in the ramified places, and then I take the ideal generated by these two elements, 1 minus sigma v EV. And what are these things? So okay, so this needs a proof that it's actually contained in ZG, because none of these elements are in ZG. This is not in ZG, this is not in ZG, but somehow the product is an ideal of ZG. What is IV? This is the inertia subgroup at V, and norm of IV, this is just sum overall sigma in IV, sigma. EV is simply 1 over, this is the idempotent corresponding to IV. Okay, so this complicated looking object, this turns out to be an ideal in ZG, and then the conjecture of Kurihara, which again we prove away from p equal to 2, is that the fitting ideal of this dual class group, the dual class group, it has this exact description. This is in fact the Sinnett-Kurihara ideal. Okay, so minus means 2 is always inverted, and you take the part on which complex conjugation acts by minus 1. Okay, so this is a nice thing. You have an exact description of the fitting ideal. Okay, at least the initial fitting ideal. Now, how does this imply the statement that we want? Well, if you just take S to be the smallest thing that you need to take, and from that you can get other things, then theta st hash h over f, this is simply theta s infinity t hash h over f. I don't know if I'm writing h over f much, but v in s ramified 1 minus sigma v ev. Okay, so if you just so to see what this means, this is exactly kind of what it means. Now you might say, well, what is sigma v if v is ramified? You just take any lift in the Galois group, and because you are multiplying it by the norm element, this is all well defined. Okay, so this is my sketch of how the statement that we are interested in follows from Kurihara's conjecture. Okay, so this is a nice description. Yeah, so theta s infinity, I said, this appears here. This has the interpolation property that if you take theta s infinity t, this you simply get your L chi 0 with s infinity and t decoration here. So you're not removing any Euler factors. Okay, because there is hash here, you don't have chi inverse like in Somnath's talk. Okay, so that's another refinement. This one is maybe more natural question than the one that Somnath had stated, but I'll recall that, and I'll in fact recall a modification of I'll in fact state a modification of the statement that Somnath had made in terms of these Ritter-Weiss module, and these modifications are the one that we can prove. So instead of my S, I'll take the following set. This is all V in such that V divides. So now from now on, I'll fix an odd prime P. So fix an odd prime P And so everything will be p-adic from now on. So I take for my sigma this particular set. So this is my replacement of S. Okay, I don't use all the ramified places. I only use the ramified places that are above P. So this kind of sets are not generally considered in Iwasawa theory or special values conjectures. And then I modify my T as well. I make my T bigger. So I don't get rid of all these ramified places. I just put them in, I just shift them from S to T. Okay, so this is my replacement of S. This is my replacement of T. And then the theorem. So this is the main, okay, so the main technical result we prove, from which all others are derived, obtained, is the following theorem, which says that the fitting ideal over ZPG of, now this is the Ritter-Weiss module that was mentioned in Samit's talk, and today's talk will be all about kind of constructing this. Okay, so this will be a ZG module, and the P here just means I'm tensoring it with ZP. This is generated by the following Stickelberger element. Okay, so again, this sigma sigma prime, this simply means that when I evaluate it at a character, I get L values with Euler factors at places in sigma removed, and then some sigma prime smoothing. Okay, so this is the main technical result that we prove. Okay, so what is the plan? So the plan for today is to give construction of this module nabla, and then reduce proving this statement to constructing certain cohomology classes. And then next time, the plan for the second talk will be to construct a cusp form needed for construction of the required cohomology class. So that will be the second lecture, and the third lecture will be to actually construct that cohomology class using the cusp form that we have from the second talk. Okay. All right. So today's first task is construction of this nabla. Okay. So maybe I will mention this again next time, but the reason why we modify the set like this is, I mean, at least so far as I am concerned, I had no deep intuition in taking this thing, these particular sets. These are the sets that worked for the construction of cusp form, as you will see next time. And so these are the ones that we used, and we said, well, let's see where this takes us, and you just, that kind of leads you to make such a conjecture, which is just modification of this conjecture that Burns, Kurihara, and Sano made, and then that turns out to be the right thing. Okay, so at least the way we were led to these sets is just because we could construct cusp form only with these sets, as you will see next time. So maybe that's, I just wanted to mention that if these sets seem very unnatural to you, that S and T kind of is the usual thing what people take in Iwasawa theory or Bloch-Kato conjectures, but not these sort of sets. Okay, so I'll construct this nabla and give its properties. In particular, it will tell you that to prove this theorem, we require construction of a cohomology class with certain properties. Okay. So to begin with, we fix a S prime. This is finite set of places of F, which satisfies a bunch of things, and this is some auxiliary choice that we make. In the end, the construction of nabla is not going to depend on this S prime. Okay, so that's a small lemma. We prove in our paper that the construction in the end is independent of whatever. So we want sigma to be contained inside S prime. Okay, so all the it contains at least the places that ramify and are over P, and the Archimedean places, and it can contain something else, but it's not. It doesn't intersect with sigma prime. Okay, so those are the first two things. Then the class group, the sigma smooth class group, this thing is trivial. I don't know if this was defined, but maybe I'll define it in a moment. And then the last thing is, if you take intersection, if you take all the decomposition group for places above S prime in H, then this gives you G. Okay, so you can always take a large enough S prime, which is still a finite set, so that these two properties are satisfied. Okay, so this thing is just the sigma prime smooth class group of H, in which you kill all the classes that are coming from S prime. Okay, so maybe I'll just write it here and then erase it. So this thing is sort of class group of OH1 over S modulo TH. So something, yeah. So that thing. So if you want here, it's the class group that corresponds to extension of H, in which places above S split completely, and you allow tame ramification at places in T. Okay. All right. So that's the class group. And so what is the right? So we want to construct this nabla, right? All right. Yeah, I mean, in some sense, these three talks are again going to be independent. So today it's all going to be about construction of nabla and properties of it. Next time it's going to be about modular forms, and then in the last lecture it's going to be about Ribet's lemma. So this may be the most unfamiliar and so maybe slightly technical talk, and next time modular forms, and everybody knows that, so that's going to be fine, I suppose. Okay, so Ritter and Weiss constructed this to understand Tate sequences from class field theory. So let's begin with that. So you start with this kind of simple sequence where you now I forget what I denote. Yeah, I think I denote it like this, but I don't know why the first. So I'll do this construction over Z, and then everything will be tensored with ZP to get to the statements. Okay. Okay. Yeah. Well. All right. So this is just the augmentation map, which was denoted by epsilon in Samit's talk. He had relative augmentation, which was denoted by epsilon, but okay, this is also augmentation map. And this is the kernel of augmentation map. And this gives, you apply, okay, so C H is the ideal class group. And then you apply Hom of something comma CH to this, you still get an exact sequence, and you take its G cohomology and you get an isomorphism. So get an isomorphism which is denoted here by delta from Hom delta G CH to H2 of G Hom CH. Okay, so Z CH. Okay, and this thing is simply, so you can take this as an exercise if you like, all these claims that I'm making. So this is an isomorphism because Hom ZG to CH is cohomologically trivial. Okay, so all its H1 and so on are trivial. This thing is simply the X group X1 of delta G CH. Okay. All right, so there's this fundamental class here that comes from global class field theory, and that corresponds to some extension here, which we denote. So this corresponds to some extension, which I'll denote by, I forget whether I write 1 or zeros everywhere. Sometimes I write 1, sometimes I write zeros. Okay, this is supposed to be some sort of O, I think, in the paper. But anyway, this is one kind of extension that comes from class field theory, global class field theory. And we have a corresponding thing locally as well, but locally you have a much nicer description of it, explicit description of these things. So, so let me put it here. Then I'll combine the two sequences. So I'll write it down again on this board. So there's the local analog gives yeah, so ideal class group would just give you HW star and then some mysterious object in between and the local Galois group, right? And there's also corresponding thing with the unramified stuff. So this is, and I'll tell you what these VWs and WW is. Okay. All right. So I'll define what these VWs are and so on. So okay. So these are just the things that come from fundamental class in local class field theory. And what is the description of this? So if I take the Weyl group of these, the maximal abelian extension. So always, you know, what I'm doing throughout is I'll fix a place V of F and then something above it, okay, which I'll denote by W. So this will always be the case unless I don't think I'm using it for anything else. And then GV. So this let me call pi V, and then the corresponding thing for unramified extension. Okay, so this let me call it pi W, and now I can almost define what this is. Sorry, there's on the board kind of various notations would look like the same thing. So I sub capital V, this is not I sub small v, which was the inertia group. I sub capital V, this is the augmentation, the absolute augmentation ideal for this W H HW ab over FV. and then I sub pi v, this is the relative augmentation ideal. So augmentation ideal for the map pi sub v. Okay, so pi sub v induces a map from the group ring ZW to ZGV, and you take the kernel of that. That's this augmentation ideal, and this is just the absolute augmentation ideal. So V, V sub W, this is denoted, this is just defined to be this thing, okay, pi V. And then W is just the corresponding thing, but with the second map. So I'll just write it down. Pi sub capital W. Okay, so this is the thing, and then this is all due to Ritter and Weiss, by the way. So I should, we just modify it slightly. They don't have this sigma prime in there. So sorry, I should have written this. Well, this is all essentially following what Ritter and Weiss do in their paper. Yeah. Yes. Oh, I mean, yeah, so it's kind of modification of the absolute Galois group. So you, so for instance, yeah, here you would, HW, and then there's a, okay, so I don't know how to. Sorry, which sequence do I want? Yeah, okay, let me do it. H. So these are all local fields, and then this thing is simply the Galois group of some algebraic closure of a finite field. So this is isomorphic to Z hat, and inside this there is Z. So you just take the inverse image of that, and that's the Weyl group here. Okay. Yeah, I mean, it just behaves better somehow. Yeah, okay. Sure. Oh, this is, yeah, I have to erase this one. So I'll leave. What fell down? I'm not sure. Something fell down. So yeah, okay. All right. So these are, so now I have to compare these two, the local thing with the global thing. And the way to do, the way I do this is, okay, so for each V that I'll be considering, I have fixed a W above it. Okay, so you fix W above each V of F. Okay, and that will be fixed, and in the end things won't depend on this choice. So that will be clear from the definition itself. So let us say that yeah, so a piece of notation for each V, yeah, so for each W, if MW is a GW module, then I'll denote this. You know, it doesn't matter whether I sort of do it over V or W, because for each V I fixed a W. So this notation will simply mean I take product over all V's I induce from GV to yeah, this maybe just to be consistent. Right? So this is just the notation for inducing this over all whatever V set of V I'm taking. Okay, so now here are the objects that I want. So V will be built out of all these things, and W will be built out of all these W's. So V is simply, you take all V in S prime, VW. So whenever you are in S prime, you take this thing which comes from local class field theory. But if you are in sigma prime, then you take something different. You take the principal units. Okay, so what is this? These are all X in OW, such that X is congruent to 1 mod W. So these are all principal local units. If you are in neither, so S prime union, this is a disjoint union. If you are in neither of these two, you simply take OW star. Yeah, I don't know. Sometimes I denote star and sometimes I write cross. So it's the same thing. What is W? So again, if you are in S prime, but not in sigma, then you take your W sub W. Yeah, all these are with tildes, sorry. Okay, and if you are in sigma, then you just take the augmentation ideal. Okay. And then as a substitute for the ideal class group, I need something which I call J. So again, built out of the local ideal class groups. So J is, so if you are in sigma, then you simply take HW star. So you're going to kill everything here, I guess. So, and if you are in sigma prime, then you have to allow tame ramification. So you take UW1. These are the principal units, right? And if you're in neither of them, you just take OW cross. V not in sigma union sigma prime. Okay, so there are these three objects, and so we have this short exact sequence built out of just those, putting together those short exact sequences. Okay, and then we have the other one from the other board. This is O, and then this is delta G. Okay, so there are maps in this direction. These maps just come from sort of local global compatibility of class field theory. So this is just some kind of local global compatibility. The local fundamental class are compatible with the global fundamental class, and that's what this is. Okay, so what is the result that Ritter and Weiss proved? They proved something about these maps theta. Okay, so they proved that this middle theta is surjective. So maybe I should give a different name to it. So theta. Yeah, I think I call this theta W, and I don't give any name to this. Okay. So lemma theta is surjective. Huh? No, this is not the square. This is some kind of O that is here. Yeah, I said it when I wrote this, that this is some O. Okay. I don't know how else to write it. Okay. All right. So the only slight difference between what Ritter and Weiss prove and what we do is our V is slightly smaller. They don't have this sigma prime modification. So for them, you wouldn't have principal units. You would just have units. Okay. But nevertheless, this map still turns out to be surjective, and essentially the same proof works. What you do is you take your sigma to be S prime, and then you would know that this map is surjective and this map is surjective. So the middle thing would be surjective. And by changing your sigma to S prime, it doesn't change V at all and doesn't change the map. So this proof is actually not, I mean, this is not hard to show. Okay, so theta is surjective. So what this gives you is the following sequence, exact sequence. So this gives, so this is our first step towards defining Nab law. Okay, I don't know if this was defined, but I'll define it in a minute. These are sigma units which are congruent to 1 modulo all primes in sigma prime. V theta, W theta. Okay, so what is this? This is just kernel of theta. So this is simply Snake's lemma. Snake lemma. Yeah, sorry. Sigma prime. Sigma. So this is Snake lemma. Okay, and this map is surjective. So again, this is an exercise in class field theory that the quotient of this is exactly the class group that I wrote down there, just by definition of all these things, and the kernel of this are these units. So these are sort of all x in OH 1 over sigma cross such that x is congruent to 1 modulo all places in sigma prime. So let me write it this way. Okay. So this is one of my sequences I need. So I can erase that thing coming from global class field theory. So yeah, I mean, in this part, like it's kind of all following Ritter and Weiss. We simply just take the correct objects from their thing and note that these are the ones that are useful. Okay, so here's a small, perhaps an exercise that you can do. So for V unramified in H over F, WW is isomorphic to ZGW. And in fact, the isomorphism is also very nice. So you take sigma V, this is Frobenius minus 1, this simply goes to 1. And you can remember this was some augmentation ideal, modulo augmentation ideal times relative augmentation ideal. And this one is just generated by element sigma v, Frobenius -1, and that goes to 1. So you can show that this actually is an isomorphism. And I'm going to use this in some sort of mildly interesting way, which is the following. So what I do is I define another thing, which I call B. This is all V in S prime Z G. So these are just simply a bunch of copies of ZG. Okay, because we are going to get a bunch of with this isomorphism, we are going to get a bunch of copies of ZG here, right? And then in other components, it's not quite ZG, but something close to the augmentation ideal. Okay, so right, one way of thinking about this is kind of V in S prime Z. Right? You just take you just induce them from GV to G. To G, right? So we have this this short exact sequence, and what is this Y? Y is simply so in all components in S prime minus sigma prime. Sorry, in all components except in all components except those in sigma, W sub W matches with B, right? So what is left is only some things in sigma. So we in sigma Z, right? So this is like the this is with tilde, free abelian group generated by places of H above sigma. So this is kind of all just maybe easy. Then from here you have this map that I had before, theta W, and you can fill this diagram in the obvious way. So here it's just identity on each component. So it's just taking the sum of all these things. And this is augmentation map. So the co-kernel is Z. Okay, so you have all these things, and you can, so it's kind of defined in a way that everything commutes. And again, you use snake lemma. So this thing is surjective. So again, snake gives that a short exact sequence like this. So B theta with Y theta to 0. Okay. So this is my, so yeah, star and then double star is what I use to define Nabla. Okay, so these are all kind of all the maps are easy. You just have to work them out, and everything falls into place. So they wanted to define these state sequences for units explicitly. I mean, so Tate kind of writes this problem down about explicitly defining some sequence related to the fundamental class in this famous article called Number Theoretic Background or something. Yeah. So that's what they do kind of explicitly. So I think that was their, I think eventually their aim is to apply all these things to all these conjectures of Chinburg, this omega conjecture. That was their eventual goal, but okay. So putting these things, so okay, so there's so I compose the two maps. So there's a map from V theta to W theta and then V theta. This is not exact, of course. So co-kernel of this thing is defined to be the Nabla. Okay. So that's the definition of nabla. You take the map from V to B and then take the co-kernel of that. So that's my nabla. Okay. So you have this map from V theta to W theta and the map from W theta to B, and the co-kernel is nabla. Okay. All right. So what do we get? Just by putting these two sequences together, we get O H sigma prime star. So this goes to V theta, and then we had W theta there, but I replace it by B, and so the co-kernel gets replaced by nabla. Okay, so this is one exact sequence of use, but maybe the exact sequence that's kind of more relevant to what was said in Samit's talk is the following. So you get, right? So if okay, let me just write it down. This is just some diagram, chasing the diagrams around. So y theta is just the kernel of this map from, right? Yeah, here also I use. So this is just kernel of this map. So you take the free abelian group generated by all places of H above sigma, and you take the augmentation map to H, and you just, so these are just degree 0 elements in that free abelian group. Okay. So this is the thing that kind of Samit alluded to. He said the L function should see, well, the algebraic object should see regulator as well as class group. And so this is the algebraic object. Okay, it sees regulator through this because this is isomorphic to unit group in some sense, and then you have the class group. So this is our nabla. Okay. All right. So that's the construction of nabla. All right. Now I'll tell you about some of its properties, in particular how it's related to Galois cohomology. Sorry, is this the definition? No, so I haven't used anywhere that it's a totally real field yet, actually. So, but I did not say it explicitly because in the end, yeah, I guess only when I make the statements there, kind of, I need to use that it's totally real. Yeah, everything I is saying here is true generally. So, okay, so let me write down the first property, which is kind of very easy, and so, but yeah, I'm not going to say anything about the proof. So I think it was mentioned in Samit's talk when he defined fitting ideal, what a quadratic presentation is. So let me remind you. So let M be an R module. M is said to have a quadratic presentation if it has presentation of the form, finite presentation of the form, just Rm to Rm to M. Okay, so you need to have this kind of thing. So this is maybe Okay, maybe. Yeah, so maybe it's more appropriate to define it over local rings, and then this thing becomes a presentation of nabla, which is locally quadratic. Okay, so lemma. Again, this is kind of proved in Ritter and Weiss, but without all these modifications, and we just go through and check that the modifications work. So V theta sub P, B theta sub P to nabla sigma prime sigma H sub P. This is a quadratic presentation of ZPG modules. Okay, so these are all ZPG modules, and so this is the quadratic. So you just have to show that this is free of some rank and this is free of the same rank. This thing is easy, right? So figure out what it is. It has rank sort of sigma elements of number of elements in S prime minus 1, and you have to show that this is also free of the same rank. Okay, so this is just some computation that one does. So that's one property. Well, why is this nice? I forget if this was mentioned in previous lectures or not. If your module has a quadratic presentation, then it means that its fitting ideal is principal. So this implies that actually, let me be careful here and just do what I need to do. I forget the precise. So I'll take minus part of everything and then say that. Okay, so sigma prime sigma H minus is principal, is a principal ideal. Okay, so that's the corollary, and so that's kind of important in our, if you want Ribet's method to work, you better have principal ideals. Okay, otherwise it's kind of, it seems hopeless. I mean, yeah, this is what, so when I was giving talk on Brumer-Stark in San Diego, this is what Gross told me, that these kind of things are hardly ever principal, and so nobody tried doing it at finite level because you would have to deal with non-principal ideals. But then we came across this conjecture of Burns, Kurihara, and Sano, which dealt with principal ideals, and so this seemed like the right thing to go and try to do with Ribet's method. Okay, so having a principal ideal is absolutely essential in Ribet's method. Okay, so that's the first property. The second main property is about the second main property is about connections with Galois cohomology. So in the last 10 minutes or so, I'll do this connection with Galois cohomology. Okay. So first lemma, this is just inflation restriction and the fact that you're away from p equal to 2. So and here now I'm using, I think, I mean, for taking minus parts, and so I'm using that I'm dealing with totally real fields, but yeah, whatever, the definition of nabla was completely general. Module n, just this Galois cohomology group is isomorphic to, when I apply the restriction map, I get an isomorphism. Yeah. Okay, so So this is just some inflation restriction that you work out and prove that the kernel and co-kernel are both trivial. Okay. So why am I doing this? Well, so now for simplicity, let me put M equal to the class group, so I don't have to write this again and again. Maybe even with a minus here. Okay, so let me do that. Right. Okay. So, so if I take H1 GFM, this is isomorphic to H1 GHM fixed by G, but these are just G homomorphisms from GH to M, right? Because GH, of course, acts trivially on M, and so there is a canonical homomorphism here, which is you go from GH to, okay, so we had F, we had H here, and then we have L, whose Galois group is this thing, CL sigma prime sigma H, right? So this is the maximal abelian extension of H, which is unramified outside sigma prime, totally split at primes in sigma, and at most tamely ramified at places. Okay, so this goes to Galois group of L over H, and then from that to M, because we are taking the minus part. Okay, and sort of, this is the reciprocity map, and taking the minus part. So this is the art in reciprocity. So this corresponds to some element lambda in here. Okay, so we have this very explicit Galois cohomology class here, and I can take its restriction. So for all V, lambda V is restriction of lambda in H1 GFM to H1 GVM. Okay, I'm just restricting it to these local cohomology. Local Galois cohomology groups. Okay, so this is sort of completely independent of what this nabla was. Now, how is this related? Well, nabla is an extension class in the following group. So this is so nabla gives an element in the following thing. So X ZG minus Y theta minus M. Okay, but remember, so we are taking minus part, and minus acts trivially on the minus part of this is trivial, right? Complex conjugation acts trivially on this. So this thing is isomorphic to, well, I mean, this thing is equal to X ZG minus, and Y can simply be written as sort of inducing from GV to G of Y. Okay, and then the minus part of that. Okay. So now you just use Shapiro and get V in sigma ZGV minus Z half M. Okay. Sorry, this should have been, this is not Y, this is Z. Yeah. I can write Z 1/2 as Z minus if you like. That's the way minus is defined. And this thing now is simply sort of V in sigma H1 GV M. Okay, so nabla gives me a class in this, and the result is that this class is same as the classes given by lambda v's. So that's again that's the somewhat difficult calculation in recurrent wise, and again it works with all the modifications that we do. So maybe I'll write it as a theorem. Okay, so nabla in this thing H1 GVM is same as these lambda v's. Okay, so that's again, so all these things are very explicit. So you can do all these explicit calculations and get this. So this is a very Galois module theoretic kind of computation that people like Ritter and Weiss would do day in and day out. Okay, so how much? Okay, maybe let me just write a couple of sentences and stop. And I'll start with this theorem next time. Maybe I should call it a proposition, but so let A be a ZPG algebra. Then to give a surjective map from nabla sigma prime sigma h extended to A to n. This is A module. It is enough to give kappa. So this is what Samit was saying, that it's enough to construct a Galois cohomology class with certain local properties. Okay, so it's enough to do this and such that. Okay, so these are the two sentences I'll write and then stop. So what are the? I did not tell you what the action of GF on n is, but I'll recall this statement again next time. So I'll do it more carefully next time. So what are you need to prove two properties. One is kappa is unramified outside sigma prime, at most tamely ramified at sigma prime, and locally trivial, so stronger than unramified, so locally trivial at sigma. Okay, so that's not surprising because you want it to be related to the class group, right? Nabla has two parts. One is the regulator part and other is the class group part. So this takes care of the class group part in some sense. And let N0 contained in N be a submodule generated by image of this restriction by kappa restricted to GL. This is in H1 GL N, which is simply hom from GL to N. So you get a homomorphism from GL to N, and its image will generate some submodule. Let me call that N0. When N mod N0 is generated by some generated over A by these elements XV, some XVs. Okay, so this kind of takes care of the unit part, the Y part. Okay, this takes care of the class group part. This takes care of the Y part, and then the fact that somehow Galois cohomology is, I mean, the Galois cohomological description that we have here takes care of the extension part. Okay, so I'll recall that again next time. Yeah, I'll stop here.
Okay, if there are no other questions, let's thank Mahesh again, and we will meet again at 4 p.m. for the next talk.